Projectile Motion.
Promise you the world again, everything within my hands, all the riches one could dream, they will come from me. I hope that you could understand, this is not what I had planned.
We use 3 different demonstrations to explain projectile motion. Here are the materials we used for our demonstrations.
I need more time, just a few more months and we'll be fine. So say what's on your mind.
Okay. Projectile motion is an object being projected or thrown through the air with only the force of gravity acting on said object. A rule of projectile motion is that mass has no effect on velocity or time, assuming the initial velocity is 0. We exemplified this rule by dropping 3 objects of different masses from a window, all at the same height, and them all falling into the ground at the exact same time. Yep.
Hi everyone! You can see that there is inclement weather today, so I have to have an umbrella. But we're about to drop some objects from that window up there, and it's 3.5 meters high. So the first object we're going to drop is a Clemson basketball. Not just any basketball, a Clemson one.
Woohoo!
Okay, so I've got time from when it drops to when it hits the ground down here. Okay, Sarah, you ready?
I'm ready.
Ready, set, go. That is 0.7 seconds.
Now we're doing a ping pong ball. Ready, Maddie?
Ready?
You tell me when.
1, 2, 3, drop. Oh my goodness, it's the same time. 0.75 seconds.
Wow. Now we're going to throw Zoe and see how long it takes. Just kidding. His toys, little Miss Piggy. See how long it takes. Ready, Maddie?
Okay, 1,
1,
2, 3, drop. And again, 0.75 seconds. This is crazy. Okay, now we're going to drop all 3 at the same time just to prove that no matter the object's weight, it's always going to drop at the same time, and that means that all 3 objects have the same velocity. So, Sarah's going to drop Miss Pig, the Clemson basketball, and the ping pong ball at the same time. Ready? 1, 2, 3, drop. Oh my gosh! 0.75 seconds! Can you believe that?
Here we have a written out procedure for the ping pong falling from the bookcase. Next we'll have Maddie explaining it and how it happened in reality.
Okay, so we have our ping pong ball here, and we're measuring the time it took to hit each one of these 15 centimeter increments, and we have 10 data points, full of 10. So the total distance is 1.5 meters, which is 150 centimeters. So we just drop the ball in time at each point of the projectile motion. So the ping pong ball dropping and recording points demonstrates projectile motion.
Okay, so during our experiment, as we said before, we had a bookcase, which was 1.5 meters, and we separated it into 10 equal increments of 15 centimeters, or 0.15 meters. So what we did is we had, from the beginning, we had a ping pong ball starting from the top of the bookcase and going down, and at each increment we would measure how long it took to get to the 0.15 meters. So what we knew, because of projectile motion, is that the initial velocity is 0 meters per second, because it's stationary. From there, we had to figure out what the final velocity was. We knew that the bookcase was 1.5 meters, and it took 0.54 seconds to get from the top of the bookcase all the way down to the ground. Okay, going back a little bit, acceleration is equal to gravity in projectile motion because gravity is the only force working or acting on the object. So we know that acceleration in this experiment is negative 9.8 meters per second squared. Why is it negative? It's negative because we're going down from the top of the bookcase to the bottom, which is the ground. So from there, to find the final velocity, we plugged in the equation acceleration equals change in velocity, or final velocity minus initial velocity, divided by time. So we plugged in numbers that we already knew. Negative 9.8 meters per second squared is equal to final velocity minus 0 divided by 5.4 seconds. Then we went and we did 0 crosses out, and we have negative 9.8 meters per second squared times the 5.4 seconds, and that equals the final velocity. And from there we figured out that the final velocity in this experiment is negative 5.292 meters per second.
Okay, this is our chart of the time it took to get to each 15 centimeter increment. And so we figured out that our independent variable is the vertical distance. So that's like the meters, okay? And the dependent variable is the time it took to get to each vertical distance. And so now we've graphed it with the distance on the x-axis and the time in seconds on the y-axis. Okay, we plugged in our data to a graphing calculator, and we linearized the graph to find our mathematical model. The mathematical model is 5.151 x squared. So that means that time is directly proportional to the square of distance.
Zoe, let's revisit. Ready? Projectile motion.
Get it! Go get the toy!
You got it.
A Nerf gun can also exemplify projectile motion because as the Nerf comes out of the gun and into the air, it projects as I will show you.
Woo! There it is.
Let's go again. 1, 2, 3. Projectile motion. One more time. 1, 2, 3.
Good job. 3 trials! Look at it! It's all the way in here!
Okay, so through a couple different experiments and just messing around with objects, we figured out that projectile motion is, as we said before, objects going through the air with only the force of gravity working on it. So we did that through, off of the bookshelf we had a ping pong ball dropping, and as we showed in our equation, we saw that acceleration equals gravity, which is negative because it's going down as the Earth does with gravity. We also saw as we dropped 3 different objects out of a window, and we saw that they all fell within the same time frame. Then we showed a Nerf gun, which has an object just projecting through the air and landing. So, oh goodness. Okay, so overall we figured out that projectile motion shows the rule that mass has no effect on acceleration, time, and velocity because of gravity.
I'm thumbing my way to North Carolina, staring up the road and pray to God I see headlights. I made it down the coast in 17 hours, picking me a bouquet of dogs.